Hey everyone, it's Bradley Bush again with another algebra video for you. Today we are talking about partial fractions or partial fraction decomposition. First, we'll give you kind of a bird's eye view of what's going on, maybe 30 seconds. Then we will do an example of prime repeated quadratic factors, finding the partial fraction decomposition of a rational expression with prime repeated quadratic factors. Let's get going. So remember when we were adding fractions a long time ago? So we had two fractions, right? And we wanted to add them together, and we eventually got one fraction, and that was this one here. So we got a common denominator because the denominators weren't the same. The 2 and the 5 weren't the same, and so we got a common denominator, added them together, kept that same common denominator as the bottom, and voila, we're done. Well, that's really all we're doing here, but we're doing that in the reverse. And let me keep going, and you'll understand what I mean. So adding rational functions, so adding fractions that are now a little more complicated, they have polynomials in the top and the bottom instead of just numbers. So you still get a common denominator, and you still go from here in this case, we have two fractions, and we're subtracting them to get one fraction. We still get a common denominator in both of the fractions, and then we subtract them. We have the same common denominator in the bottom, and we go to 1. So adding rational functions, just like adding fractions. So what are partial fractions? Well, good question. Here's the punchline. Partial fractions, that's when you take a more complicated expression, say like this here on the right, the x plus 14 and x minus 4 and x plus 2 on the bottom, and you decompose it into little bits and pieces that are added and subtracted together. Sometimes you might have 2, sometimes you might have more, but you're just saying, hey, this big fraction, I think we can come up with some smaller fractions that we can add or subtract together and get this big one. And partial fraction decomposition tries to find those. So again, adding and subtracting rational expressions goes this way, goes from the left to right. But partial fraction decomposition goes the opposite. It starts at the end and kind of breaks it apart into a bunch, maybe 2, maybe 3, maybe 4. It just depends on the problem. Breaks it apart into some smaller fractions. So there are 4 different types of partial fraction problems. We're dealing with the prime repeated quadratic factors one. Here's our problem. We want to find the partial fraction decomposition of, in the numerator, we have 5x cubed minus 3x squared plus 7x minus 3. In the bottom, we have quantity x squared plus 1 squared. So the first thing we do is we find all the unique factors. For us, this problem is great for us because we only have one unique factor. It's x squared plus 1. It appears twice, and we want to know, is it quadratic or linear? Well, it's quadratic because the 2 on the x. So it's x squared plus 1. The square tells us we have a quadratic factor. So because we have a quadratic factor, when we set things up, we'll have linear factors in the top. So we have ax plus b and cx plus d. Those are linear factors because the x on each of these has 1 as the highest power. So if we had just had x squared plus 1, we would have not had this last term. It would have been gone. We just would have had ax plus b, and we would have had the x squared plus 1 in the bottom. But because we have repeated factors, we have to have a term here for each of the repeated factors. So this is x squared plus 1 to the first power. This is x squared plus 1 to the second power. If this had been on the left, had been x squared plus 1 to the third power in the denominator, then on the right, we would have had a third term that would have been x squared plus 1 to the third power. So there's a little pattern that you follow there. So now that we've created our problem setup, and again, the a, b, c, and d, those are the numbers we're looking for as we go through the solution process. In the end, though, that will be the answer, the A, B, C, and D. And we'll come back and plug them in here, and we'll have our partial fraction decomposition. So apparently this fraction on the left can decompose into two smaller fractions on the right. That's the hope. So now we just start into the process. So now it's just kind of grinding through the steps. We need to get a common denominator and add the two fractions on the right together. So let's see what we're missing. If we're looking at this, well, it looks like here, the first term here, we're missing a x squared plus 1. So let's add that. And let's make these green. If we multiply top and bottom by x squared plus 1, then now we have x squared plus 1 squared both in the denominator on the left and on the right. So we've got a common denominator, and we can now add them together into one fraction, and we keep that same denominator in the bottom, just like we did with our fractions at the very beginning in our little overview. So we should probably do some algebra, right, and FOIL this product here out. So when we have ax times x squared, what does that give us? Ax cubed. When we have x squared times b, that gives us bx squared. Let's now do, it's kind of hard to decide what color to use, you know? First world problems, right? 1 times ax just gives us ax. 1 times b gives us b. Now we've multiplied that term out. Now we have just the cx plus d still hanging out, so we'll bring that down. All right, so we need to now kind of organize things. So let's get everything together that has a cubed on the x. And luckily we just have one term. How about squareds? We only have one term, bx squared. How about terms with an x? We have ax and we have cx. So let's get those together. We put them here together. And then all the terms without an x, we have b and d, and we put those together as well. So we've kind of gathered everything together. All the x cubed terms together, all the x squared terms together, all the x terms together, and all the terms without an x together. And why do we do that? Well, we want to compare coefficients. That's the whole point. You might be wondering, why are we doing all of this? It's to compare coefficients. So here for this, the x terms, we notice we have an x in both of these. Let's pull that x out, and it comes out. We'll put it in behind here, but we have an a plus c out front. Now we can compare terms, because the reason we like the big picture here is we have an equal sign, right? We have two things that say they're equal. This large thing on the left and large thing on the right, there's an equal sign in the middle, and that equal sign says these two sides are equal. Everything's equal. So the denominator is the same. That's good, right? So the numerators have to be the same if the equal sign holds. So what is in front of the x cubed term on the left? We've got a 5. So what is in front of the x cubed term on the right? A. So if these two terms really are the same, a has to equal 5. And we can put that down here. That's our first equation. A must equal 5. For these two things to be equal, a must equal 5. Let's compare the squared terms now. On the left, we have -3. On the right, we have b, positive b, by the way. So we know b must equal, -3. How about we compare the terms with an x now? So on the left we have +7. On the right we have a plus c. So we know that a plus c must equal 7. And then our final step is to compare the terms without any x. I ran out of highlighting colors. That's not good. On the left we have -3. On the right we have b plus d. So b plus d must equal -3. And there we go. We have our system of equations. We can solve the system of equations and get a, b, c, and d, and then plug them back into our original setup, and we're done. So we can see from these equations that, first off, a equals 5 and b equals -3. So those two variables are already solved. Now we can plug a equals 5 into equation 3 right there and solve for c. And then we can plug b equals -3 into equation 4 right here and solve for d. So let's do it. If we take a, and we know a is 5, and we solve, let's subtract 5 from both sides. That gives us c equals 7 minus 5 is 2. We have solved for c. Perfect. So let's plug b equals -3 into equation 4 and solve for d. So we have -3 plus d equals -3. Add 3 to both sides, and we get d equals 0. Excuse me, I've got the hiccups here. So let's state all of our answers, just so we remember. So a equals 5, b equals -3, c equals 2, and d equals 0. We're really close to being done. So we have our original setup. Remember, we started out and we said we think we can decompose this large rational expression into the sum of two. Hopefully the sum, we're not sure. But we think the sum of two different smaller fractions. And we only had 2 here because of our problem setup. Now we've found a, b, c, and d. And we can literally just write out our answer. So we have a equals 5. Then we have the x. And b equals -3. So we have -3 here. C equals 2. And we have our x. And d equals 0. So we can just drop it off. And that's it. Right? We've just decomposed 5x cubed minus 3x squared plus 7x minus 3 all over quantity x squared plus 1 all squared. We've decomposed that into 2 smaller fractions that are added together. 5x minus 3 over x squared plus 1 and 2x over x squared plus 1 quantity squared. So how could they make this harder? Well, they could throw in other factors, or they could throw in a non-repeating linear factor, as we see here. So in this case, you see that we have a quadratic that's repeated 3 times, and we have a non-repeated linear. So in our problem setup, the repeated quadratic, again, would have a linear top here, and I have 3 of them because I have 3, there are 3 times that this factor appears. So I have a term for the first, second, and third time it appears. And then I have an extra term for my linear. And with linears, we just put a single constant in top. We don't have to put a linear factor in top. So that's it. Hopefully this was helpful. I've got a lot of other videos on the other types of partial fraction decomposition. If you want to check those out, you're welcome to. Hope you enjoyed it. If you did, please subscribe to the channel and have a good day.